class. This is Math 102, Chapter 1.2 on problem solving and critical thinking. We will break this lecture into two videos. Now, Chapter 1.2 is on estimation, graphs, and mathematical models. Our objectives with this section is to look at using estimation techniques to arrive at an approximate answer to a problem, to apply estimation techniques to information given by graphs, to develop mathematical models that estimate relationships between variables. Now let's look at estimation. Estimation is the process of arriving at an approximate answer to a question. Our methods of estimation are using rounding of numbers, using graphs, using mathematical models. We're looking to round whole numbers to start. The first thing we're going to look at when we look at rounding whole numbers is to look at the digit to the right of the digit where the rounding is to occur. If the digit to the right is 5 or greater, we will add 1 to the digit that needs to be rounded. And then we will replace all the other digits to the right of the one that is of interest with zeros. If the digit to the right, however, is less than 5, we do not change the digit to be rounded, and we replace all digits to the right with zeros. The symbol approximately equal to is right here. This stands for approximately equal to. We use this when rounding and showing an estimation or showing a number that is close to but not necessarily equal to the answer when doing estimations. Now, our first example says rounding a whole number. We want to round world population. 7,843,169,634. We want to round that to the nearest 100 million. Now, the rounding here is done for you, but let's go through the process. The 8th place is the area and place that we want to round to. In order to round to this location, we must look at the number before the 8. In this case, it is a 4. Because that 4 is less than 5, it tells us that this 8 does not need to be changed. Therefore, all we need to do is rewrite the numbers to the left, the 7,800,000,000, and then all of the other numbers to the right of the area we want to round to need to change to zeros. Which leaves us with an approximation of 7,800,000,000. Now, example 2 takes the same world population and it rounds it to the nearest million. So now we need to look at the millions place. That's right here at this 3. In order to round to this place, we need to look at the number that comes before it, the number in the hundred thousands place. In this case, it is a 1. The 1 tells us that this 3 in the millions place stays the same, and all numbers to the right of it will drop to 0. So we will rewrite all numbers to the left, the 7,843,000,000, and we will put zeros because we are rounding for everything to the right. Example C says we want to round the world population of 7,843,169,634 to the nearest 100,000. The 100,000 place is right here at this 1. Now we look at the number that comes before that, the number in the 10,000s place. That is a 6. That 6 is greater than 5, greater than or equal to 5. So 6 tells us that we need to round this 1 up to a 2. And then we will allow everything to the right to become zeros. So we will write everything to the left just as it is, except we have now rounded this 1 up to a 2, and we're going to drop all other digits to zeros. So we wind up with 843,200,000. Now, let's look at the rounding of the decimal part of a number. We want to round 3.141592, which are the first 7 digits of pi, as follows. We want to round to the nearest hundredth place. In order to do so, we need to highlight what's in the hundredth place. The hundredth place is the 4 right here. We need to look at the 1 to determine what we do to that 4. Following the rules we already have set up, we know that we should just keep the 4 the same. Okay, so the 100th digit is where the rounding is to occur, right there at the 4. The digit to the right is indeed less than 5. Therefore, it does not change the digit that needs to be rounded, so we keep it as a 4. Now when we're dealing with decimals, all we do is drop off all digits to the right when we're done. So the 4 stays, it doesn't round up, it stays, and we drop the number and round it to 3.14. This would be our answer. And look there, there's our approximately symbol. So, because we rounded, this number is approximately equal to that number, which is our answer, 3.14. Now, we want to look in part B at rounding to the nearest thousands. So, 1's in the tens place, 4's in the hundredths place, 1 is in the thousandths place. Now, this number tells us how to round the 1. That 5 tells us we need to round the 1 up. So, we are going to round it to 3.142 and then drop off the remaining part of the digits. So if you follow underneath here, we highlight the thousandths digit. We look at the digit to the right, which is the 5. That tells us that that 1 needs to be rounded up to a 2. And then after we do that rounding, we drop all of the digits off to the right. And we have our approximation 3.142, which rounds it to the nearest thousandth. Example 3. In estimation by rounding, you purchased bread for $2.59, detergent for $5.17, a sandwich for $3.65, an apple for 47 cents, and coffee for $8.79. The total bill was given as $24.67. Is this amount reasonable? To check, we want to round the cost of each item to the nearest dollar. That's what we'll do over here to the right. So we have written down every single item that we have bought, and we have rounded it either up or down to the nearest dollar depending on what is in that tenths place. So bread was $2.59. We want to round to the nearest dollar. This 5 tells us that we need to round up, which is why we rounded it to $3. We look at detergent. We want to round to the nearest dollar. This 1 here tells us that, hey, we're going to keep it at 5, and we're going to let the 1 and the 7 just be zeros. The sandwich was $3.65. We want to round to the nearest dollar. The 6 tells us that, hey, we need to round up to $4. The apple was 47 cents. We want to round to the nearest dollar. The 4 tells us that we just drop everything and let it be zeros, because we do not round up. We only round up when that number is 5 or greater. We look at the coffee, and the coffee was $8.79. We round to the nearest dollar. So we're wanting to round that 8 to the nearest dollar. We look at the 7. The 7 tells us to round up, so we round up to $9. Now we take those estimations, because they're easier to add than our original numbers here. We take those estimations and add them up. 3 plus 5 is $8, plus 4 is $12, plus 0 is still $12, plus 9 is $21. So our approximated expenditure here is $21. The reason we do these estimations is it's a lot quicker to add up these numbers in our head than it is to try to add these numbers up. Not many people can add up these two-digit numbers here, or two decimal place numbers here, in their head quickly and efficiently, but many people can add single-digit numbers or whole numbers in their head quite efficiently. Now, once we do that estimation, what you'll notice in that estimation is that some of these are rounded up, some are rounded down. The ones that are rounded up kind of displace what was rounded down. So we lost 48 cents here when we rounded down, but we also added 35 cents here when we added up. So they kind of cancel each other out in the estimation, your losses and your gains. Now, estimations are going to be close, but they're never going to be exact. You are going to have some error there, but it gets us in the ballpark. What you'll actually see is our estimation of $21 was pretty close to our actual cost of the item. The bill of $24.67 does seem high compared to our $21 estimate. So when we actually do take the time to add up the prices of all 5 items here, the true bill is $20.67. Very close to our estimated cost. So somewhere in the bill we were overcharged. But because we were able to estimate what each thing cost, we were able to highlight, without doing all the small math, that hey, something is probably wrong in this bill. Now let's look at circle graphs. Circle graphs, also called pie charts, show a whole quantity that is divided into parts. Circle graphs are divided into pieces called sectors. The figure on the next slide shows a circle graph that indicates how Americans disagree as to when old age begins. Let's have a look at that. So, Americans' definition of old age. 32% think that a decline in mental functioning indicates old age. Reaching a specific age was seen as a definition of old age by 14% of people. 1% of people don't know what the definition of old age would be. Retirement was seen as the definition of old age by 9% of people. Becoming a grandparent was seen by 3% of people as a definition of old age. And a decline in physical ability was our biggest section of the pie, at 41% of people believing that is the definition of old age. So, we want to apply estimation techniques to a circle graph. According to the U.S. Census Bureau in 2020, there were 249,019,818 Americans 25 years and older. Assuming the circle graph on the previous slide is representative of this age group, we want to A. use the appropriate information displayed by the graph to determine a calculation that shows the number of Americans 25 years and older who define age or old age by a decline in physical ability. And then in part B, we're going to use rounding to find a reasonable estimate for this calculation. Okay? So let's look at A. We want to use this to determine a calculation that shows the number of Americans 25 years and older who define old age by a decline in physical ability. The circle graph indicates that 41% of Americans define old age as a decline in physical ability. So, if we want to use and find the actual number of people who think that old age is defined by a decline in physical ability, we would need to take that 41%, that percent in this pie over here, and we would need to multiply it by the actual number of people we have, which is 249,019,818. Okay? That would be the math that we would actually need to do. Now you could easily do that on a calculator. But let's assume that we were trying to estimate this, maybe perhaps in our head. If we were to do that, we would use rounding to find a reasonable estimate for this calculation. So the rounding that we are going to use here is we're going to round that 40%, that 0.41, we're going to round it, that 41%, down to 40%. And then we are going to round this 249,019,818, we're going to round that to 250 million is what our estimate for that particular number here. Okay, so here we rounded to the 10 millionths place, which was our 4 here. Our 9 told us to round that up. Okay, now what we could see by this is it's really easy to multiply 4 times 25, whereas multiplying 41 times 249,019,818 is reasonably difficult to do in your head. But this multiplication here, 4 times 25, can easily be seen to be 100. We move the decimal place one location because of this decimal here, and we easily see that our estimation here is 100 million. 100 million. So, just going through the steps here. So, approximately, because we estimated, approximately 100 million Americans 25 years and older define age by a decline in physical ability. This concludes the first half of the lecture. Please come back next time to see the video on the second half of the lecture, which will begin with the estimations of graphs, including bar graphs. Y'all have a good afternoon.